just to quickly introduce the setup, there's a few main cameras that you'd want to have a look at. Namely, the first would be the screen share, which you'll see in the top of your Zoom window. If you click through between the meeting and the screen share, you'll see the notes that I'll be talking out of for the bulk of the lesson. The other one would be a camera that is pointing at my notebook for any handwritten notes that we do. It would be probably easiest if you pin that tab so you can refer to it quite quickly. Just simply right click on that window and click pin. That'll make it always the active window for you, and it makes it easy just to switch between the two required cameras. If there's any questions as to how that's all working, let me know. Maybe hop off mute, put a text in the chat, any of those. But for today's catch-up class, we're going to have a look at two main topics. One is going to be the introduction to polynomials up until polynomial division, and the other will be on transformations, namely how we can determine our own sequence of transformations. We'll get through the content on that, and then I'll see which of the two topics we should probably spend our time on. So, without further ado, let's give it a shot. So, from the screen share. Polynomials. So what is a polynomial? It is simply a sequence of terms that are x to the power of something. So in this case, you can see you've got a x to the power of n, b x to the power of n minus 1. You have a sequence of x to the power of n type terms. And the degree of a polynomial is a key term. Specifically, it is referring to the highest power of that polynomial. So in the example provided, x cubed plus 2x plus 1 would be considered a third degree polynomial, since the highest power in that sequence is 3. Otherwise, that would be known as a cubic. You'll notice that a lot of different functions will have similar names to them, or sorry, multiple names that refer to the same thing. Kind of like how a quadratic could be considered a second degree polynomial. As for how we solve polynomials, anything beyond a quadratic, and even quadratics included, you'll typically want to factorize. Now, I tried to exclude quadratics there simply because you do have stuff like the quadratic formula and completing the square as secondary options, or I guess other possible options for solving those. But when it comes to more complicated cubics, you don't really have that, more complicated polynomials, I should say, you don't really have that luxury. The main way that you can solve things via algebra is going to be through factorization and the null factor law. That's basically all you have before having to resort to your CAS to solve things using more computer effective methods rather than things that we would do by hand. But yeah, just a quick recap, null factor law just simply means if you have a product of factors like this that equals 0, any of those factors could be the reason why it equals 0. So you just go term by term, equate everything to 0, and then solve. That's the gist of polynomials. You pretty much get it into a factorized state, and then you solve each of them via null factor law. Sometimes you might have nonlinear factors in there, like in this case we've got a quadratic. It just means you're going to be solving that the same way you would solve any other quadratic, which in this case I've done either a factorizing approach or completing the square, both of which would get you to this state here. And sometimes that quadratic may or may not even have solutions. If it's entirely above the x-axis or entirely below the x-axis, it'll never actually cut, and so for those reasons won't have any solutions. You can prove that there are no solutions by checking the discriminant of the quadratic. So discriminant, just as a reminder, you've got the terms a, b, and c as the coefficients of any quadratic. The discriminant is b squared minus 4ac. That's where all those terms are coming from. If it comes out to be negative, you have no solutions. Any questions so far on any of that? Just a recap of the polynomial stuff. Cool. One of the things you've probably already come across with quadratics, or even linear sometimes, would be this idea of equating coefficients. And that's simply where if you have two functions that are identical to each other, what you can do is sort of go term by term, and because they are equal to each other, it means that every single term in one polynomial, or any function for that matter, needs to be the same as every other term in that function. So for example, these both have an x cubed. For them to be the same, 4 must be equal to a. In algebra, you just equate the two terms together and simplify everything else. In this case, this one does not have an x squared, but this one does. So the only way for these to be equal is if this b was 0, or in other words, would completely cancel out the x squared term. And we don't have to look at the constant. We already see they're the same, plus 8. Now, it doesn't usually show up in this way. That's pretty easy and obvious. What you'll typically get is you'll have some sort of function and you'll be told, write it in this form, or make it look like this in some way, shape, or form, or compare the two. If we have a look at one of the textbook examples really briefly, you'll get something like this. Here's a quadratic, here's another quadratic. Make them the same. There's a similar version of that in here as well, but that's a bit harder to see because there's a few steps before you get there. That's the sort of ways in which you'll see those things before. You can solve this in a couple of different ways, but the main method by which you're trying to solve it is simply make both functions look the same. So in this case, f of x is in the polynomial form, it's fully expanded, whereas h of x is in the completed square form, or otherwise referred to as the turning point form. Pick one of them. So either complete the square on this, which is what I've done here, and then you can easily compare, that's a complete square, that's a complete square, easy. The other alternative would be expand this all the way out, and then you'll be able to compare them directly. So what that would look like would be here, right? So you expand out this square bit here, getting you to this, distribute the a all the way through all those terms, and then you do the whole equating coefficients thing, where you got an x squared here, a 6x squared here, a is going to be 6. You got a 2abx here, a negative 24x there. Negative 24 must therefore be 2ab, and well, you already know what a is from here. So that's kind of just another of the comparing term by term. This one's also more or less the same. You see you have very similar looking things here, but this is like pretty much drag and drop, right? You got a 6 there and an a there. That's going to give you a is 6. You got a negative 2 there and a b there. That's going to be b equals negative 2, and so on and so forth. Just looking at terms once they're in their similar state, and then just one for one mapping them to each other. Sometimes you need equations to do it. Other times you can just look and then it's there. That's some basics around polynomials. Any questions so far? And, feel free to leave things in the chat as well. I'll revisit them afterwards if you don't want to hop off mute. But okay, so we've talked about how polynomials are best solved if we can factorize them. That is, however, a big if. How do we factorize them? Because not all polynomials can be factorized, and even those that can be, it can be quite difficult to find the factors if you're just sort of guessing and checking your way through it. So we need a better approach, or we need a approach, at least. This is where polynomial division started having applications. So it might not be immediately obvious why polynomial division does what I've suggested it does. The idea of polynomial division is simply it's like a way to simplify a division of two polynomials. So you've got a cubic divided by a linear in this case. You can go through this whole procedure to simplify it down into that. So you can simplify it down into some other term, a sequence of terms. Why does that matter? Well, let's have a look. So, actually, yeah, why does it matter first? Let's do that. So, why does doing this matter? Well, if we think about what we've achieved, we've got this left-hand side is equal to this right-hand side. This left-hand side contains a polynomial that is normally quite tough to solve. If all I did was multiply both sides by my denominator, what I would now have would be a series of factors on that right-hand side. Or in other words, I've turned this polynomial, this cubic, into a series of a quadratic multiplied by a linear, which, if we have a look at a similar example, would basically be that. I've got a linear multiplied by a quadratic. I can now solve that, but I can't really solve this one. So because those two things are now equal to each other, I've taken it from a tougher form to solve into a much easier form to solve. That's what this ends up doing and helping us with. How do we actually achieve it? Well, it's a sequence of essentially 3 main steps that you're going to loop over and over again until you meet some exit condition. So, just a bit of terminology. I'm using n and d for the numerator and denominator respectively. What you're essentially going to do is set up your polynomial division framework as follows. The denominator will go on the left-hand side, and the numerator will go on the inside of that division operator. What you do from here, you look at the biggest term, or the leading term, on the inside, and divide it by the leading term of the outside. That's step 1. So you take this thing, x cubed, divide it by this thing, x. That's going to get you x squared. If you want to, you can show some working on the side, but if your mental math is good, just put it directly in there. This is not required. This is just to sort of show you, what am I doing? You don't need to actually have this in your own working. Yeah, so the result's going to go up there. From there, you take whatever that result was for that step and multiply it through by the entire denominator, so the entire outside thing. So it's going to give you the x squared multiplied by the x plus 2, and whatever that result is going to go underneath. Ideally, you would write it in a way where everything is lined up. So the x cubes underneath the x cubes, the x squareds underneath the x squareds. Most of the time, it's going to just sort of naturally do that. We'll have a look at one example where it doesn't quite do that unless you go out of your way to do it. But yeah, okay, so we took this thing, multiplied it through this, and that got us this result. Last thing you do, perform a subtraction, right? Now, what you're essentially doing is taking this whole polynomial and subtracting this polynomial. I've gone out of my way to put brackets around these things to remind yourself and myself that this subtraction doesn't just hit this term, it also hits this term. So for instance, what I'll often see is sometimes people will go x cubed minus x cubed equals 0, cool. Then they'll do x squared plus 2x squared, which is incorrect. This negative sign has to always be applied to each of these terms. And my method of trying to remind people to do that would be by putting brackets around the whole thing. So what you should instead be doing is x squared minus 2x squared, giving you minus x squared there. This is a sequence of zeros, so everything else will just sort of drop down. Whenever you subtract 0, nothing really changes. So that's the 3-step loop there. It is divide the 2 leading terms and chuck the results up here. Grab that result, multiply through, and put that here. Then subtract that result from this, getting you the next starting point. Anything about the initial 3 steps there to clarify further? Cool. So what you're essentially going to do is repeat all of those steps with where you left off last. So we've now got a quadratic as opposed to a cubic. So we're going to, once again, look at the leading term here, divide it by the leading term over on the left-hand side. Left-hand side is never changing, so this operation pretty much always becomes the same thing over and over again. The only thing that's changing is the start, what you're actually starting off of. So in this case, it's negative x squared divided by x, giving you negative x. You take that result, so remember it's specifically this result. It's not just the whole thing on the top, it's whatever the specific result was from that step is what's getting multiplied through here. Performing multiplication, put it down, again, trying to keep everything lined up, just, you know, kind of like what you're used to with basic subtraction tables in, I don't know, sub year 6, earlier than that perhaps. Yeah, wrap it up in brackets, put your minus sign. I'll just pay special attention to what this looks like, because I know when there's a lot of negatives in here, people start to get confused. So this would read as follows: negative x squared minus negative x squared. So you've got a minus and a minus right back to back. That'll cancel down into a plus, leaving you with negative x squared plus positive x squared, which is why that cancels down. Very similar thing over here. Negative 14x minus negative 2x. Double negative cancels it up into a positive 2, which is why we've gone from negative 14 to now negative 12. And again, that's just a 0, so that's just going to drop down. That was the second loop of that. We did our division, so divide up until there, multiply through here, subtract. You'll notice that every time we do this, we're basically knocking it down by a single power every time, at least in the case of linear. Sometimes you knock it down by more. We're going to essentially keep going until we can't go any further, which is going to happen in this next iteration. So leading term divided by leading term, that gets us that. Grab that, multiply through, that's going to put this down here. Subtract, and you can see since those things are the same, it's just going to cancel down to 0. Once you have 0, that is the ideal answer. That's what you want later on when it comes to using this to solve polynomials, and we'll explore a little bit more about that later in next week's classes. This is referred to the remainder, so it's basically whatever's left over after division has been performed. And the reason why 0 is good is because that means that what you found, what you divided by, was a factor. It perfectly is divisible into the thing you started with. Whereas if you are left with anything other than 0, there's going to be some remainder afterwards. And you guys might remember that from when you would do long division, or if you did long division. You would do your division of your two numbers and you would get left with some remainder. Exact same thing here, but there's now x's involved as well. As for how you would express that remainder, what you would do, instead of just having the thing on the top as your final answer, like we did before, what you'll now have is, in addition to that, you'll have the remainder term divided by whatever the divisor is. So I'll just sort of compare the two. So this one, we ended up with x plus 1. So we have our x plus 1 as our what's referred to as the quotient. And then you have the remainder term, which is this divided by this. As compared to, in the previous example we just had, there was no remainder. This was the quotient. So you got quotient plus 0, so we just don't bother writing it. Those are the differences there. Those are the main options or outcomes that you can get from a basic polynomial division. Anything to clarify further on that? Okay, I'll briefly touch on this one because these are quite long things. You can divide by non-linear things. In this example, we have a quadratic. It's the exact same procedure. Get the two things that are leading and divide them by each other. But in this case, because we've got different powers, we're going to get a different result here, right? Instead of having a quadratic, we now have a linear up top. And the other nuance would be when you go and multiply this all the way through, unless you're intentionally spacing things out, your nice and neat vertical lines are going to start being not so nice and neat. So one thing you could potentially do would be to put a placeholder of 0 in here and then write the x over there, just so that when you do your subtraction, you can look directly down vertically. But it's not the end of the world. Again, this is how I do it, but you know, I've done this a lot, so I can just sort of be like, yep, the x cubes with each other. There's no x squared, so I just chuck that down there, and there's two x's that I got to do the subtraction on. So the main thing is that you're keeping the same power terms with each other. However you want to go about that is up to you. Cool. All right, that's polynomial division. Try to go through it at a bit of a faster pace, since for many of us that's the second time we've had a look at it. But if it's anyone's first time, more than happy to quickly clarify anything else before we move on. Easy. Okay. So next up is the final part of transformations, which is how to determine a sequence of transformations, or in other words, try to figure out what would be required for us to get from one function to another function in terms of what transformations we're applying to it. This is the last part of transformations. However, you don't need to have already done transformations to understand this, except for a tiny bit here, which I'll put a bit more detail into. There's a couple of main ways you can do this. One is to use this so-called point notation, which uses a lot of x dash, y dash stuff. You might have seen it before if you've done transformations. You'll see things with x's and y's in them. You'll see x dashes and y dashes. All that simply means is whatever has x and y in the function is considered where you're starting from. What's the original function? Wherever the x dash and y dash are is the new function that you're trying to get to. That's literally the only background you need for this bit of notation. Everything else you could learn off rip from here. So how do we figure out how to go from one function to another function? Well, that's going to be this little framework here. If you follow these steps exactly as written, you'll get these questions right every single time. Just keep in mind it's not the only way to do it. So if you know your own way of doing it and you're happy with doing that, feel free to continue doing what you're doing as long as it's working for you. But rather than talk high level, let's have a look at an example. Okay, so we're trying to go from f to g. In this case, we can see that f has a decent amount of transformations on it. It's got a dilation factor, it's got a horizontal shift by 1 and a vertical shift by 6. And well, this is just a basic truncus. It's got nothing on it. So the first step is simply to get our notation the right way around. These are functions named f and g, which, is fine, right? As long as you know you're going from f to g, that's cool. My preference for notation has always been whatever function you're starting with, write with x and y. So instead of saying f is equal to all this, say y is equal to all that. And whatever the new function is, in this case g, that's going to get y dash and x dash. The reason why I wouldn't use g as is because both of these have x in them. What you want to have is a differentiation between the y and x from one function and the y and x from another function. So if you really wanted to, you could say gx dash, but yeah, again, all we're trying to do here is get our head straight on what's what came from where. From there, once you've got your notation the right way around, look at both of these functions and rearrange everything that is a y transformation to the y side. So in this case, the left-hand side. The only thing that has any transformations is going to be the original function. This has got nothing attached to it. It's just a truncus. So we're going to do our subtraction of 6 and our division of 3. That would be the dilation factor of 3 and the vertical translation of 6, respectively. If it's challenging to figure out what's a y transformation and what's an x transformation, well, first, do more practice because you will need to be able to spot these things quickly. But two, in a pinch, pretty much just shift everything over to the left-hand side that you can before you start breaking down the fundamental function. And what I mean by that is, there's really nothing else you can do to this before it stops looking like a truncus. Like, this still looks like a reasonable truncus. If you were to put the denominator to the left-hand side, it doesn't really look like a truncus anymore. If you expand this out, not going to look like a truncus. So it's a nice little litmus test for like, how much am I shifting over to that side? Yes, the real reason is get the y stuff on the y side, but as a nice little cheat, just move as much as you can before the function stops looking like a function. So fair enough on how much we're moving over to that side. Cool. Okay. From there, we're going to create our equation. Now, how do we create this equation? We're going to look at the two results that we end up with. So remember, we're trying to rearrange both of these to get the y stuff on the y side. It just so happens that this one didn't actually have anything on it. So this one looks like that, this one looks like that. How we create our equations is we make the left-hand sides equal to each other. So in this case, y dash is equal to y minus 6 on 3. That's there. And in the other case, you've got this right-hand side is equal to this right-hand side, which is written here. Now, the reason I haven't taken the entire right-hand side is because the real thing that you're trying to do, or that you actually care about rather, is the transformations. We don't actually care that this is a truncus, we just care that it's been shifted right by 1, and that this one hasn't had anything applied to it at all. So because that's the only thing we care about, we just want to bring the transformations with us. Now, it's not wrong to make the entire right-hand sides equal to each other, because those will just cancel down anyway, right? Like you can imagine, if you have this is equal to that, all you would have to do is multiply both sides by the denominators and then square root. You get right back to here anyway. So even if you do it the long way around, it's not going to matter. It'll be a bit slower, sure, but I'd rather you be slower than not get it at all. But yeah, that gets us our two equations. You're just looking at the left-hand sides, making them equal to each other, and then looking at the right-hand sides and making those equal to each other. Clear enough? This is one of the toughest topics of methods, by the way, so if you do have anything to clarify, let me know, because this is one of the hardest. Alternatively, if you are getting it well, then congratulations. One of the hardest topics is no longer one of the hardest topics for you. The next step is a bit of rearranging, so you're just going to make sure that x dash and y dash are on their own. In this case, we're lucky. There isn't anything else actually even on these x dash and y dashes. We're already there. In some circumstances, specifically where the new function has transformations on them, so the x dash and y dash will have some stuff on it, then you're going to have to rearrange. We'll show you an example of where that's applicable. So what do? Well, x dash is the same thing as x minus 1. So if x dash is the new x, then what you have in point notation is you say you're starting from this point xy, and you're mapping it to this new point, which is what x dash and y dash are. You're just grabbing those and putting them in that spot. And you explain out of the end of step 2 and step 3, end of step 2, end of step 2. End of step 2 is the rearranging of getting the y stuff on the y side. Is that what you wanted me to explain again?
I think it's probably just step 3.
Step 2 is the rearranging to get the y stuff on the y side.
Yep, I think I get it.
Oh, you got it now?
Yep.
Cool, yep. Easy. Yeah, okay, cool. So what do you do from here now that you have your finalized x dash y dash? What are these new things? Well, in some circumstances, that just is your answer, right? Not all of the time they're going to ask you to write it in a sequence of words, right? Like this is, for all intents and purposes, the transformation that you need. In a lot more common circumstances, they want you to write this out in a sequence of words. So what do we do here? This is where there are multiple correct answers. I talked at length in all the various ways in which we could have correct answers in the previous time we did this class. I'm not going to do that here because it's a recap. I'll just give you one way, and if you're curious to see all those other ways, it's in the recording for that class, or alternatively you can look at the pre-recorded scripted versions of these, which are like 10-15 minutes, a lot easier to get through. So here's one of many ways you could do this. The way my preference has always been is to start by making sure that the x and y, so there's no coefficients on that x and y. You just want them as raw as possible. Technically, we've already done that, but to make it a bit more obvious, I'm going to bring that divide by 3 out as a factor of a third. Nothing's actually changed here. There was no coefficient on the y as is. I've just tried to make it as obvious as possible that there is nothing directly on the y. The coefficient of this y is currently 1. That's what you're looking for both the x and the y. Then from there, write the transformations in this order. You do your translations first, then your reflections, then your dilations. If you've done transformations before this class, you might have heard your teacher say do it in the opposite order. There is a different approach that does that. That is not this approach. So if you're doing it that way already, stick with that if it's fine for you. This is a different way of doing things with this exception up here. And again, if you want the nuances around when to use what, I've mentioned where you can look for those. But okay, so we do our translations, then our reflections, then our dilations. So what does that actually look like? What you got to keep in mind is that when it comes to x and y dash notation, everything works as you would normally expect, which is that any negatives on an x should shift it towards the left because you're decrementing x values. Any positives on the x should shift it right. Any negatives on the y should shift it down. Any positives on the y should shift it up. That's different to function notation, where when we had our polynomial, right, x minus 1, we would normally think of that as a shift right by 1. When it's in the function, things are a bit reversed for x. When it's in x dash y dash notation, things are back to what we would normally expect things to be. That's the only weird. This is why transformation is the hardest thing. You've got to, or one of the hardest things. You've got to pick your battles as to when you're in function land or when you're in x dash y dash land. Things work slightly differently. But okay, so any pluses or minuses on a term are translations. So one way you could do it if you're doing translations first is to say a translation of 1 unit in the negative x direction. That's this thing. Followed by a translation of 6 in the negative y. That's this. Then you would go to reflections, of which there are none. Reflections are just a negative sign attached to the x or the y, respectively, of which there are none, so we can skip that over. And then dilations. That's going to be any multipliers on the whole thing, of which there is just this one here, our dilation factor of a third along the y-axis. The other way to describe that would be to say a dilation factor of a third from the x. There's two main ways you can write that. Just a question. Sorry, I couldn't hear you for a sec. Is the translation, reflection, dilation order the order of examiners? So there's no specific order that's preferred. Yeah, you can do this in many different ways. What I will say is because there are so many different ways of doing it, what they do is they don't force you to do it a particular way, at least in words. What they'll do is, like for instance, here's 2 ways of saying the exact same thing. What they will do is they will pick whatever the first one of those bullet points is and actually write that in for you as the answer. They'll say, don't give me all 3 of them. I'll give you the first one and you write the next 2. And the reason why they do that is because, well, if this is here first, you can't start with this anymore. So you now have to adapt your approach and do things in a slightly different order. So yeah, it's good to know. Yeah, for now, I'm just teaching one main way of doing it. It's good to still know all of them. For the scope of this class, we're going to look at least one way of doing it, but I do highly recommend you check out the previous stuff, or I guess as we do more practice, we can maybe look at the other ways of doing it, because they will cheekily force you into one way or another. But yeah, so I guess just to quickly highlight again, one reason why even within doing it this way, there's still multiple ways you could do it, namely because the x and the y stuff is totally independent. You could do all the x transformations and then all the y transformations, as long as you're staying within the particular order for the x and for the y. It doesn't matter what order you do them in. So in this case, I've done x, then y, then y. In this case, I've done y, y, x, right? But in every time, it was always translation, dilation, and then because you got to the x, you've got to start back to translation. So as long as you're keeping towards that, that's the main thing there. It's tricky stuff, this transformation stuff. So it's one of those things where you just got to practice a lot of them. And once you get good at one main way of doing it, then you can start being like, okay, what are the other things we could potentially do? There's a full other example in here, which is the opposite way. You're starting with something with no transformations on it and getting to something that is transformed. The reason why this is in here isn't because it's really any different. It's literally just to highlight that when you get to this stage, one of the stages was to rearrange for x dash y dash. If you remember from before, we didn't need to do it. It was already on its own. In this case, we can see it's not on its own. So you do have to do a quick rearrange and then go through the rest exactly as we've seen before. It's literally there to show you like literally one liner working. The rest of it's just a nice another example to look at. Okay, so that's using the x dash y dash stuff. That's using the point notation. Any questions on how that works? Cool. Yeah, and there's another method on top of that. So, like, just to give you context, within point notation, I can think of 4 separate ways you could do point notation. And within this, there's really only sort of one way to do this. So really, like if you add it all up, you've currently got like 5 different ways you could answer the same question. This one is different enough to where it's probably worth still touching on. I'm just sort of mindful of time, because when we do these recap ones, they tend to be with a lot of me talking. I think we should be able to touch on it at least. Okay. So what we did there was look at a very rigorous step-by-step instruction of when you have these questions, do this every single time, you'll get it right every single time, as long as you're following the letter of every single step. Just read it top to bottom, do it exactly as written, and you'll get those questions right all the time. This approach is a bit more freeform, kind of like how algebra is a bit freeform. You know, how we rearrange things isn't necessarily set in stone. There are fast and slow ways of doing it. There's no like hard and fast rules that you have to stick to, as long as you're doing legal operations, anything's on the table. That's kind of what this is. The advantage of it is that it's very fast. You can condense all of the steps in here into maybe like, well, we can ignore that step. We can condense it all the way down into maybe 3 or 4 separate operations. But you have to be good at your algebra, and you have to be really good at making sure that where you're subbing in things is where they should go. It's worth practicing because it will make you faster, but it's also more prone to error. Let's have a look. These aren't really steps anymore. These are guidelines. I can't really give steps for this. It's a bit more freeform. So, first thing you'd want to do, kind of like how we saw in the initial of polynomials, just make sure that both functions look the same. Right? Like if you're looking at these 2 functions here, this one's completed square, this one's expanded. Who knows what's going on in this thing, right? It's dilate factor of 4 at least, but I don't know what the vertical translation is for this bit, and surely not the horizontal translation. Typically, you're going to default to whatever form makes it easiest to see the transformations, which is going to be the completed square form. So we're going to take this nasty looking g of x, complete the square on it, and now we can easily compare where we're starting and where we're going. That's the first guideline. In fact, that could be a step. You pretty much have to do that every single time. Next up is a reminder. So what we're going to be doing is a sequence of substitutions to eventually transform the first function into the second function. We're going to repeatedly add, subtract, multiply, divide a sequence of numbers until we make that happen. Anything that impacts the y will never impact the x, and vice versa. We'll see what that looks like in a bit. As for what to do, this is where you're going to do things in the order of dilate, reflect, translate. So this might be another reason why you've heard it the other way around, because it's absolutely applicable to this. We'll see why as we go through it. So, starting with our dilations, we want to compare the 2 functions that we have, so f and g. This one has a dilate of 3, this one has a dilate of 4. If I want to go from 3 to 4, I have to figure out what number do I multiply 3 by to make it into 4. The hack for that is just make whatever this thing is the denominator, and whatever this thing is, oh, sorry, the other way around. Whatever that thing is the numerator, and whatever you're starting with the denominator. Because then if you, for instance, in this case, you're multiplying by 4/3, the 3's cancel, and then the 4 will come through. You're turning f from having a dilate of 3 to a dilate of 4, but what you'll notice is that it hits the translation term. So that 4/3 will also hit the vertical translation. Remember, this is a y dilation, and this is a y translation. Anything that impacts the y will impact all of y. Well, I shouldn't say all of y in all cases. Point being, whenever you multiply an entire function, you hit the entire function. We would then look for other dilations, of which there are none. There might be a dilation in here a little bit, would be represented by a division. Very rare for polynomials, though. Then we would look for reflections. If we're looking at f and g, you can see there's no negative signs on any of those x's, so we're happy enough. Then we look for translations. So in this case, we're looking at the vertical ones first. I've just got to figure out what I've got to add to this to make it equal that. In this case, it's 8 on 3. Add it up. Cool. Awesome. We got there. This is where remembering how to sub things in matters a lot. So we want to get from x minus 2 to x minus 1. This is a shift right by 2. This is a shift right by 1. So we would know if these are on the same graph, all I've got to do is take this thing and shift it left by 1. How do I do that? I need to put something in the x spot such that when this simplifies, it looks like this. So I want to go from x minus 2 to x minus 1. The only way I can do that with additions or subtractions is to just add 1. Minus 2 plus 1 gets you to minus 1. That makes them the same. Why can I just shove that in there? It's because I'm performing an x translation. This is the spot where x translations go for quadratics. So this isn't really algebra as such. It's not like you can't do this in algebra. You can't just shove a thing in wherever you want to. Because we're applying transformations, we can be picky on where these things are going. You just have to be very careful of where you're putting them, because this is where the errors lie. People absolutely accidentally do things in different orders. But okay, after that full sequence is done, we'll see that we actually end up exactly where we wanted to end up. What you then do is you look at all the numbers that you used and just write those out in the order that you did them. That's it. We started with this dilate factor, or you could say from the x on this alternative way of pronouncing that. Then we did this translation, and then we did this translation. We just write them in that order. So I guess when you're doing these numbers, these transformations, maybe write something or highlight it on the side. This was this transformation. This was this transformation. This was this transformation. So you know which ones to write at the end. There was a lot of talking there, but if we think about like what was actually done, we just said, cool, we have this. I want to make this look like that, so I'll do this. Step 1. I want to make this look like that, so I did this. Step 2. I want to make this look like that. Step 3. So that would have been 3 lines of working, but you can see how much you sort of have to do in your head to rationalize what those 3 lines of workings are. All right, that's me talking for approximately 45 minutes. These recaps do tend to go for a bit. Anything in there that I should clarify? Or I guess just anything from the entire lecture before we get into some questions. If not, let me know which of these we should focus on. Most of us have done both of these topics already, so I'm curious to see which of these still need work to have a look at. We'll get a bit of a vote going. We do some questions on the x-y-. Absolutely. Yeah, transformations, perfect. Yeah. It's the hardest topic. I was expecting it. Cool. Okay. So specifically with the x dash y dash notation, we can absolutely do that. I'm not just going to give it away though. We're going to do it all live together. You guys are going to collaborate. What I'll do to make life a little bit easier though is I'll drop the notes of this specific transformation set. In fact, I should probably also drop the other notes as well that we looked at, the polynomials. If you want access to all these, by the way, or if you don't already have access to all these are just a bundle on our website, just a one-time $70 thing. It's like having an extra textbook, essentially. But okay, so if you change your camera over to the handwritten notes, what we're going to do is go through one of these questions. In the meantime, what you should probably do is pull up that the determining sequences notes. That'll have the steps that we're going to follow, and you guys are essentially going to tell me what we should do to do this. So I'll just quickly write out the question while you guys get up that, and I'll even make it available on the screen share as well once I've got this written down. 2 bracket x minus 1 all cubed plus 3. 2 bracket x minus 1 all cubed plus 3. Yes, okay. So starting from the left, going to the right. I'll pull up the steps on the screen share as well if you don't want to have a copy yourself. Let's crack on. How are we going to start this one out in our handwritten notes? Going from y equals x cubed to the new cubic with all those transformations. What's step 1 telling us to do? You're allowed to be wrong. It's fine. Anyone at all. Be brave. Even just literally read out what the step is and tell me your interpretation of it.
It's just taking the two equations and then just characterizing one of them as function of f, and then the one that would be the function that would be g of x just as x dash y dash, with easier for later on.
Precisely, yes. Step 1 is just getting us to get our notation the right way around. Where we're starting is going to stay as y and x if it isn't already, and where we're going is going to get y dash and x dash in those spots instead. 2 bracket x dash minus 1 cubed plus 3. It's almost getting off the side there. Yes, okay, step 1 done. Nice. Step 2. What are we doing? Even if you don't have like concrete exact next steps, even just conceptually what we should be doing, I'll take that as well.
Wait, what was the specific question that we're working on?
So I've got it written down on the handwritten notes bit. It's at
Oh,
the
okay,
top.
yeah, I can see it. Yeah.
So we're just starting at the cubic and making our way to the other cubic. Got our notation done. That was step 1. Step 2 going to get us to do?
Just moving like anything that affects the y onto the left hand side, and anything affecting the x onto the right hand side.
That's really good. Yeah. Would you like to take a stab at what that might look like for this one?
I think it would be, is that y equals x cubed on the left hand?
It is. Yep. So that one's
Okay,
got,
so
yeah.
so I think that one just stays as it is, right?
precisely.
Uh, and then for the one on the right, I don't know if the dilation would affect the y-axis or the right axis, or the x-axis.
That's a good point. So this would nominally be thought of as a y dilation. It affects the y-axis. Any function y equals a f of x, where a is the dilation factor, whenever it's a multiplier on the function itself, that's considered a y dilation.
Yeah.
The reason why I say it's a bit ambiguous is because when it comes to polynomials, you can have additional dilation factors, but they can be factored out into here. So it's kind of ambiguous with polynomials specifically because of that factorization. Um, but yes, whenever you have a number out the front of the function, that's typically referred to as a y dilation.
Yeah.
So with that in mind, what should we do?
Wait, so I'm trying to remember the steps. So, oh yeah, you just divide by 2. So you bring the, yeah, y dash over 2
Yep.
is equal to x dash minus 1 cubed plus 3.
Okay. If you're going to divide by 2, just keep in mind the algebra laws still apply
Oh
here.
yeah.
So you would have to do that as well, but otherwise, okay, that's still fine.
Okay, and then, oh, and then minus 3 over 2.
Yeah, that's right. That's it. Cool. And again, so the shortcut here is always just shift over as much as you possibly can until it stops looking like a function. This is still a cubic. Trying to do anything more to this is not going to make it look like a cubic anymore. So that's the litmus test for if we've done everything right. So even if you are on the day like, oh, is this one part of it or not? Just shift everything over until it stops making visual sense to do it. But yeah, that's exactly as written what you do for step 2 in that. Sweet. All right.
Yeah, I was just a bit unsure about step 3 because I understood everything up to this and after, but I just didn't understand step 3 specifically.
Yeah, okay, cool. Before I just give that away, does anyone want to take a stab at trying to guess at what step 3 might be like? What do we do here? I'll give it a sec. Okay, so step 3, we're trying to get our expression of what's x dash and what's y dash. Currently we have x dash and y dash separated from the x and y's. We need to get them into the same equation. And the way we do that is with step A of, so 3A, right? Which is get the x stuff with the x stuff and the y stuff with the y stuff. Or in other words, if we have a look at the handwritten notes again, the y stuff is just whatever's on the left-hand side of both equations that you had, whatever you ended up with. These are now going to have an equal sign between them. That's the easiest way to think about it. Y equals y dash minus 3 on 2. That's what I mean by equate the y components to each other. I consider this to be a y component. I consider this to be a y component. Same thing for the x's. I'll just make it super simple. Just grab the entire right-hand side and the entire right-hand side of that one. Make those equal to each other as well. X cubed is equal to x dash minus 1, all cubed. That's the bare bones way of doing it. Grab the left and rights together. Part B. This should be terminology you guys are familiar with enough. What does Part B tell us to do, and how might we do it?
So just rearranging it. So I think, would you want y dash on its own on one side?
Mm-hmm. Sure do.
I guess. So you'd multiply both sides by 2
Mm-hmm.
and add 3.
That's it. Yeah. Y dash is equal to 2y plus 3. Smashed it.
And for the other side, just cube root both sides
Yep.
and add 1.
Perfect. Nice. Yeah. There is a bit of a shortcut with this whole equating thing. I'm just not going to get into it because that seems to be where most of the confusion is. If you just do right-hand sides, you'll get there. Cool. Okay. Yeah, that's part B, all the way done. Step 4. Yeah, let's see how this wording looks. Step 4A. What are we doing? Had a bit of trouble trying to figure out how to word this in the best way. So if you guys aren't getting it, that's partly my fault for not wording it properly. But let's see though. Yeah, I want to take a stab at what that means. You can even, if you have a copy of your notes, you can even have a look at what that step looks like. Taihan, I noticed your mute was bugging back and forth a couple of times. I don't know if that was a tech issue or not.
I am not sure. So, but yeah, I'm not 100% sure on this step.
Yeah, that's fine. So basically, sometimes your sometimes your x and y's will have coefficients still on them. Technically, they always do. There's a coefficient of 1 on anything there where there is technically no coefficient. But in this case, it's pretty obvious there's a 2 on the y, right? That's a coefficient on the y. What we want to do is rewrite it in a way where there aren't coefficients. This is technically referred to as factorizing, so that would be the correct terminology. You want to factorize any coefficients off of the y and the x, of which case there is only really one way to do that here. You would take the 2 off of the y and you factorize here. I think I've played with both wordings and both are equally ambiguous, so I guess it's just one of those things where you have to see what it is. But yeah, all we're doing is taking a coefficient of 2 off of that. There are ways of solving this where you don't do that, but then you have a completely different step B. We're not going to get into that now. We're just going to get you down one way that works. So yes, we're doing an additional step here, but that's only so that we can make sure we have one guaranteed way of doing things. That is step 4A achieved. All we're going to do now is express our sequence of transformations in English. This set of statements is the transformations. This is the new y and what you're doing to the old y. This is the new x and what you're doing to the old x to get there. We're going to use English to try and describe it. How might we do that?
For y dash, it's a dilation by factor 2.
Yeah, dilation 2. Now, you can explain that in two different ways. You can say from an axis or along an axis. What's
I
the
think you would
feature?
say from the x-axis.
From x. Yes, that's good. The other way could have been along y. Both of those are valid, but mainly you'll see this.
And then I think vertical shift of 3.5, 3/2 units.
Yep. Vertical shift, 3/2 up. Sure.
Yep.
What else?
And for for x dash, it's just up by 1.
So you'd probably say right for this one because it's x.
Oh, sorry. Oh, bad. Yeah.
Yeah. So we've got a unit of 1 to the right. This is shorthand. Don't do this in the real thing. Don't just use the wording that I've got in my notes. Yeah, I mean, that's good. So you've listed out the actual transformations. The only thing I'll point your attention to is in the step, it specifies do it in order of T, R, D. So basically, chuck this one on the bottom and you're happy. And then everything else is fine. You got the exact numbers and their names associated with it correct. You just got to do it in the order translate, reflect, dilate.
Wait, I don't know if I'm getting confused, but I thought there was another order where it was dilation, reflection, translation.
There is. So if you look at the screen share, what we were following was the point form steps here, which if you
Okay,
look for that one,
Yep.
yeah, it says that there. There is a variant of this where you do DRT, but you have to skip this. In fact, what you have to do is expand everything out rather than factorize everything out to achieve that. more details on that will be, as I've said a couple of times, in the previous version of the lecture or the scripted ones that I've done. The other way to do DRT would be with the function notation stuff, where you do that approach instead. So again, tricky. This is why I sort of debate whether or not I should show both or multiple methods, because that's where the confusion starts to set in. But on the other hand, you do kind of need to know how to do it a couple of different ways, because as I said in the real SAC, or specifically in the exam, I know one question in my mind specifically where they have definitely said what they'll do is they'll have like, if I go to the handwritten bit, they'll have their little script of here's what's happening. Then in the answer, they'll have bullet 1, bullet 2, bullet 3, and they fill out bullet 1 and they say, you got to do these other two. Have fun. And because they're filling out bullet 1, if it's a dilation, you kind of have to do a DRT approach. If it's a translation, you have to do a TRD approach. So you do need both, but when we're learning it, just pick one of these, master that, and only then should you try and do another one. But you do need to do both, just not right now. All right, cool. I think I've said that like 600 times enough, so I'm hoping that's the approach there is settled in enough. That brings us to time. I will stick around for anything further to clarify for the next few minutes or so. Otherwise, yeah, enjoy the rest of your days. Yeah, we'll kick off with some new stuff for Unit 3-4. I forget exactly what we're up to. Unit 1 and 2 will continue with polynomials. But otherwise, yeah, if there's anything specific you want me to have a look at, you can always submit questions or topics in the Google Forms. In fact, I know some of you might have SACs coming up soon as well. So if that's the case, definitely tell me. We'll do those stuff specifically. But yeah, I'll stick around for a bit. Otherwise, take care. Thank you.
Can I talk to you quickly for a bit?
Yeah, mate.
Sure. One second. I'm just pulling up something I got from my school.
Hey Chris, could you send the what's it called? You know the document you were looking at, the notes from Monday's class?
The polynomials, yeah, that's in there as well in the
All right,
PDFs.
all
So you
right,
got
yeah,
the,
that's just what I needed.
yeah, easy.
All right, thank you.
No worries.
Is it okay if I share my screen quickly?
Yeah, go for it.
Sorry to take up your time.
No, you're good.
So this is basically like the SAC schedule that I have for my school, because I know I was talking to you before that I think before I started tutoring about what my SAC would be like. But yeah, our schedule is a bit weird. Whereas my first SAC is actually near the end of term 2.
That's actually more common.
But yeah, I don't know. Yeah, I don't know how common that is, but
That's super common, I would say. Like,
yeah,
only very few people have SACs coming up soon. That's the rarity, I would say.
yeah,
Because yeah, what they do is because like literally most of functions and relations is stuff you've already done. Like in this entire
yeah,
section of chapters like 1 through 8, there's 1 or 2 new topics, and they are like, in fact, if I pull up the specific ones, it's going to be composite functions is new, and sums and product. So these two, like
yeah,
1D, 1E, everything else you've seen before.
yeah. Yeah, and I think it has. I just wanted to ask you, like, how closely should I follow the study design, when I'm kind of going through the textbook?
The study design, as in like the
Yeah,
literal VCAR study design.
yeah, yeah.
I wouldn't even open it. It's
Because
basically
because I'm doing like a lot of humanities subjects this year. And like they just told me to religiously follow the study design, but I don't know about
okay.
methods.
That's
I don't
interesting.
know about methods.
Yeah, methods you can practically ignore the study design. Everything, these textbooks are basically a bible as far as what questions to do,
Yeah,
as well as any of the practice sacks and stuff that I've got in there. And the reason
yeah,
why isn't because I'm great or anything. It's because I pulled a lot of the questions from those practice sacks from a bunch of different exam providers and just sort of chucked them into one document.
yeah, yeah.
So all of that's going to be the Bible. Your SAC is going to be chapters 1 through 8.
Yeah, and also differentiation too.
Oh yeah, right, because it's in, so you're
Yeah.
doing, usually it's like chapter 9. Do you get to chapter 10 diff applications? Sometimes.
I don't know. I have a planner here. Sorry, I don't know how much time you have, but I thought I'd just show you now.
Yeah, you're good.
Yeah,
Let's have a
obviously,
look.
this is kind of where we're at now. So it was funny because I think last week we were doing the transformations and then we did that in class, but I already knew how to do it, which was really
Perfectly.
helpful.
Yeah, I mean,
Yeah,
that's what we're hoping for, right? To make sure you're getting it here the first
yeah,
time, and then,
yeah.
yeah, nice, love it.
So would you say, yeah, because I know we have, let me just pull up the uh thing, yeah. Like with the class, um, like obviously since I'm doing a lot of work by myself, would you
Mhm.
say it's just good to just kind of go through everything? And I know you can like tick something off if it's done.
Yeah, yeah.
But would you say like instead of just going straight to the textbook, just kind of going through each of these, maybe watching the videos and looking at the resources?
Yeah, what's the best order to do it? I would say do as many of the questions that you can already do yourself, and as long as you're getting
Yeah,
them right, I don't really care how you're learning it. Like, get them
yeah,
right until you stop getting them right. Then you'll notice that all the modules, it should be fairly obvious to know, oh, okay, I'm doing chapter whatever, and this is where it is in the classroom.
yeah.
As long as you're able to like know which one's corresponding to which, I only look
Mm-hmm.
at those if you need them, right? Like if you could do all of, I don't know, let's say if you can do your transformation stuff, which I know you're having a bit of trouble with, but
Yeah.
if you can do them, do them. As soon as you can't, then look at that stuff and then see
Mm.
how it's done. It's meant to be
Yeah.
more of a reference, and yeah, you can learn the whole thing from scratch there. That was the idea, but
Mm.
um,
Yeah, and
if you're
I was more asking um like if I'm just say, okay, today I'm gonna look at this, okay, let's tick it off.
hmm,
And then kind of go through this because I feel like the school planner and the textbook is a bit like how do I say? It was a bit overwhelming, whereas this is a bit more like split up.
yeah, okay, interesting.
Yeah.
Yeah, I mean, whatever. Look, the whatever seems easiest for you to get into doing work, then do that. Yeah. So if you want to do
Yeah.
module by
Yeah.
module, and do like at the top of all of these, you'll notice I'll label where they are in the Jacaranda or Cambridge books
Oh, okay.
specifically.
Does it say like which part of the textbook it relates to?
Yeah. So if you have a look at like the
Okay.
screenshot that I got up now, the polynomial division stuff, it'll tell you where it is in Unit 1 and 2. It'll tell you where it is in
Yeah.
Unit 3, 4,
Yeah.
Cambridge, Jacaranda. That's
Yeah.
on all of the documents, not the
Yeah.
videos, but the documents.
Yeah.
So yeah, if
So
that works, then by all means do it that way.
yeah. Yeah. I just wanted to give you an estimate by the pace that we're working at for 3-4 methods, would you do you think we'd be slightly ahead of how fast my school's moving? I think you can see.
Hang on, let me pull it up then. So our curriculum, what have we got? So
Let me know if you want me to like zoom out or if
no,
you
it's
want to
fine. I'll
see.
tell you like what week everything will be wrapped up by. Yeah, all of diff will be covered by term 2, week 4. So that will get you to the
Send
end.
to- Yeah, that's exactly on point with my school. Yeah, yeah, yeah.
Yeah.
Because as
Okay.
soon as we hit week 5, we start integration.
Yeah. Okay. Now I think yeah, that should be exactly on pace. I think I noticed because what week are you in right now?
We are in week. We just finished week 2, so next week is week 3.
Okay, so we are literally exactly on track.
Yeah.
Okay, cool.
Okay,
Because I
that's
know
perfect then.
yeah. So yeah, I mean that's that. Now we do have a there's still a review week baked in here, huh? There is even a review week baked into our curriculum. So
Yeah.
if no one says anything, I'll just bring the next thing forward and do that, so
Yeah,
we can be
sure.
another week ahead.
Mm-hmm.
But yeah, seems like we're going to be on pace. And again, the whole point,
Yeah.
the curriculum's supposed to be secondary. If you guys have things that you want to look at before your SACs, that's going to be the
Mm.
priority.
Yeah. And I know the review period's a bit more flexible, so I'll probably try and send through like more questions.
And I mean, anytime,
Yeah.
anytime anyone has a question, I'm going to go through the top of the class at the because that'll be the most relevant thing, right? Like
Yeah.
some of you guys may or may not be doing transformations. I know you are. Some of them might not be. I know.
Yeah.
And so for that reason, that facility is there. You're not derailing the class or anything. It's
Yeah.
part of the design. I want to give you something that you can walk away with.
Okay. Yeah. That sounds good then.
Sweet. All right.
Awesome.
No worries.
Thank you so much. Have a good night.
Happy to help. You too.
Bye.